Welcome to this second session of calculus. Right, must have gone through the worksheet that I sent after the first lecture of calculus, and also a few hints that I have sent along with the answer key. So in case you're not able to work out any question even after the hint, do not worry. We will discuss those questions in the second half of this class also, some of those questions. But as you must have seen in the worksheet that I have used very simple principles of maths like ratio and proportion and average rate of change kind of concepts to solve the questions. I have not used any complicated differentiation and application of calculus type of things in those particular examples that I've sent, because that was what the worksheet was meant for. It was for very simple cases of physical quantities which depend on time linearly or stuff like that, where you can use, as I said, ratio and proportion, slope of straight line, those kind of principles from maths that you have learned in 9th, 10th itself. So not really using any extra knowledge, but just applying it in the context of these type of questions. Anyway, so hope you had a good time trying those questions and might have learned a few things. Many of you have been sending me doubts also in WhatsApp, and you would have seen that that's a nice way to resolve some questions. I can send you some hints, etc. Others who have not explored that yet, you can keep doing that, like as and when you are doing questions, exercises, or revising any part of a lecture, going through the previous lecture notes or assignments, etc. If anything crops up which is confusing you or as a doubt, you can always send it to me by WhatsApp, or if you've joined the Discord platform, even better, because it's a very organized and systematic platform for attachments and all kinds of information based on shared screens, etc., to be there in one place. So please do join the Discord link, and through that you will be able to access many things like your worksheets and recordings of the lectures and notes, etc., in one place. And also you can post your doubts in the dedicated doubt room, so we can get back to that in a systematic manner also. Okay, so let's begin today's session. So we are now coming to very interesting aspect of differential calculus, which we will learn gradually in today's lecture. Picking up where we left off last time. Now, in case you're wondering why this is basic calculus, okay, there is a more advanced set of concepts in calculus that you will be learning as part of your math syllabus, but that will be sometime after class 11th, in the beginning of class 12th. Whereas the fundamental principles of calculus will be required for us in physics right from the beginning of class 11th, really. So that's why we are covering those fundamental principles which are particularly useful in our applications in physics in this section, and hence the term basic calculus. But having said that it's basic calculus, it is not something that we can say is exactly very simple. Calculus can appear to be a complex subject, but it's also a very interesting subject. And as we understand calculus from the application perspective in physics, we will see that it becomes more and more interesting, and therefore you will not sweat over the complexity of it. Rather, you will enjoy the interesting aspect of it in its application. Okay? So that is the hope anyway from my side and from our side. So let's begin with a few quick recap of a couple of the things that we had learned last time. So in the previous lecture, we had learned the difference between the quantity of average speed versus the instantaneous speed concept. Okay. In context of motion of a particle, etc. And we had seen that average speed in general we can define as the distance covered in a certain time interval divided by that time interval. So it is, we can denote it like this. So it is defined for an interval of time. So average speed always is in context, or it is defined in context of a particular time interval. It is not defined at an instant. It is defined for an interval, T1 to T2. Whereas when we talk about instantaneous speed, the concept is a bit more abstract. We define it as delta S by delta T, but putting like a qualifier over here that the delta t should be extremely small. Okay, so this symbol means that it's tending to 0. So it means tends to 0. That means it should be very small. So we had understood this more in context of measurement in physics. For example, if we are measuring instantaneous speed using a speedometer, what the speedometer achieves is it achieves this calculation for a particular value of delta t, which might be, let's say, 1 millisecond or 1 microsecond, or might be the time taken by the wheel to make one complete rotation. So in the context of the total time of the journey, that's a very short amount of time. So we can say that, okay, more or less it's accurately measuring the instantaneous speed. But the accuracy of the measurement actually depends on how short we are able to take delta t as. The shorter the value of delta t, the more accurate our measurement will be. So that is in context of measurement. Okay, now today we will come up with a more exact definition of instantaneous. But at this stage also we reiterate the point that instantaneous velocity is not defined for an interval. It is defined for an instant of time. Okay, so it is defined at an instant, not for an interval, whatever the time is. And we had seen examples and all that. And we had also understood that this can be related with the slope of a particular kind of line that we draw for the VT graph. It is the slope of the secant line for the S versus T graph. Whereas this becomes what we call the slope of the tangent line. So we had just looked at this concept a little bit last time, albeit it's an abstract concept, especially the concept of the tangent line. So we will be looking at this in much more detail today, because that is in fact the business of calculus. The first part of calculus, differential calculus, is exactly the purpose of that operation in maths is this thing only, slope of tangent line. So again, slope of tangent line in the S versus T graph. Okay. So these are some of the ideas we had explored in the last lecture. And based on this, the questions I'd asked you to solve and all that. So we'll come back to those. Now let's get into more specific aspect of basic calculus today. So in order to understand calculus, the first thing we will talk about is something in maths called functions. And from functions, we will get into rate of change of function. So can anybody tell me what is a function? Like not the English language meaning of the word, but the mathematical meaning of the word function. In maths or in physics, what do we use the term function for?
Any expression.
Any expression. Okay, can you be a little bit more specific, like what we are trying to do using the expression? Or can you give me an example?
Sir, we use the expression to show relations.
An expression that gives a relation, right? That's what you're saying, Akmal?
Yes, sir.
Okay, relation between what now? That becomes important when we are talking about function.
Sir,
What does it relate a function?
Sir, like a function.
Yeah.
Sir, a function can be a condition.
A function can be a, sorry?
Condition.
I didn't get you, Hemal. Come again, Vita?
Sir, a function can be condition.
A continuation.
Condition.
A condition. Yeah. It can be conditional also. Okay. But okay, what does function relate? I think we have understood that a function is a relation, right? And that relation can be given by a mathematical expression or by a condition. But what does function relate? Can you give me an example of what things a function might relate? Yes, Anirudh?
It relates, establishes a relation between two variables.
Two variables. Very good. Okay. Anything specific about the variables? Like, can you give me an example of two such variables a function might relate?
X is equal to 2y, for example.
Correct. That's okay. Or something, simple like we have done in the last lecture. If we get a relation between distance and time and we plot the graph of it. So when we write the expression for distance as some formula of time, like whether we are writing it as v into t for uniform velocity, or we are writing it as ut plus half at square for uniform acceleration, whatever, but we are relating the distance. Now that is one variable in terms of an expression of time. That is another variable. So we are relating two variables. So an example of such a relationship between two variables is the relationship between distance and time. And such a relation will be called a function. Yes, Bhavika, that's correct. No, so we express the function in mathematical language like this, that if we are saying one of the variables is y and the other variable is x, then we can express it as y is equal to fx. Okay. So what Bhavika has sent in the text chat is the correct mathematical expression for a general function. Okay. A function, okay, most typically in maths, we define a function by a single equation like this, that y is some kind of relationship of x. Y and x are the default variables that we use. Okay, we can use something else also. We can say s is a function of t, or we can say velocity is a function of displacement, or anything like this. Okay, but basically one variable is defined as some expression, some mathematical expression with respect to another variable, and such a relationship is called a function. However, there's something very specific here. In this, when we express it in this way, that on the left hand side we have the variable y. So it means that y is what we call, it is a dependent variable. Okay, I'll explain what we mean by dependent in just a moment. It is the dependent variable in my expression or in my function, and x is what we call the independent variable. Okay. So this is the independent variable, whereas this one is the dependent variable. So what the function is doing is, it is relating the dependent variable with respect to the independent variable. Okay. So for example, I might take a function like this, that y is equal to x square plus 2x. This is an example of what we call a quadratic function. It's a special type of function called a quadratic function, which is a polynomial with maximum power of x or degree equal to 2. So here it means that x's value is independent. X has a value which can be chosen independently. Okay. Now you might say, why is x independent and why is y dependent? If I take a particular value of y, it should give me a value of x also. But that's not the point. This is the convention of how we write a function. In a function, whatever variable we write on the left hand side, that is the dependent one. And whichever one we write as the expression on the right hand side, the variable in that expression becomes what we call the independent variable, because we pick its value without thinking about what the value of y is, or without any boundation that what is the value of y. I don't have to I don't have to limit myself when I'm taking the value of x. I can take the value of x without any limitation on what the value of y is, or without any boundation on y. But the moment I select a particular value of x, now the value of y becomes dependent on that. Okay, because it is defined by this particular rule, that y is equal to x square plus 2x in this case. So y becomes, so y has a value which is now dependent on the value of x. It cannot be selected freely. It's in accordance to what I've selected as the value of x. So that is why we say that y is the dependent value. So it has a value dependent on a corresponding value of x. So that is the convention, that whatever variable we are writing on left hand side, here v would be the dependent variable, s would be the independent variable. In this case, s would be the dependent variable, time t would be the independent variable. Okay. So a general definition of function I can say is that it is a relation or a mathematical expression, okay, that defines the value of a dependent variable y in terms of an independent variable, let's say x. So x and y are just the common symbols that we use. We can use any other symbols also. So function is a relation, okay, or a mathematical expression that defines the value of a dependent variable, let's say y, for a value of an independent variable x. So the whole meaning of this statement is captured in this single expression or in this simple symbol that y is a function of x. That means x is the independent variable. So we can select the value of x freely, without any foundation on it. Whereas once we select a particular value of x, y is no longer a free variable. Its value is now locked into that particular rule, that however we are relating x with y. So moment we have selected x, the value of y is according to that rule. So for example, here for x equal to 0, the value of y, so I can select 0 independently without thinking of anything else. But the moment I have decided that x's value is 0, now my value of y becomes dependent on that. Y becomes 0. For x equal to 1, you can see that the value of y becomes 3. For x equal to minus 1, for example, you can see that the value of y has become minus 1. For x equal to 2, the value of y has become equal to, how much is it now? 4 plus 4, 16. Okay. Sorry, 4 plus 4, 8. Okay. So these kind of things. Okay. So this is just an example of a function. So as you might imagine, there are like literally infinite types of functions possible. Just using algebraic expressions like plus, minus, and powers, exponents, etc., we can generate literally infinite types of functions or infinite number of functions. So it's a very interesting subject in maths in itself, the subject of functions. Okay. So left hand side variable is called the dependent one, and it is defined in terms of some kind of mathematical expression related to the independent variable which is on the right hand side. So this is the convention. Okay, this is just a convention that left hand side must have the dependent variable, right hand side must have the expression of the independent variable. That is the general notation of a function. Okay. So for example, if we write something like this, that y square is equal to, let's say, 1 plus x square, this is not a function. This is not a function for two reasons, because it has not been expressed as y as some relation of x, and it's not a function for another reason also we'll discuss. Okay. Whereas if I write y is equal to square root of 1 plus x square, this is a function. Okay. But this is not a function. This is a relation between x and y, but this is not the type of relation which we call a function. Can anybody point out why this one is a function, whereas the first one here is not a function?
Because in the first one, we can say that even x is dependent on y. Because if we give a certain value of y, then we can relate it with x. But in the second one, we can say that y is completely dependent on x and not vice versa.
नहीं, but वो तो मैं second वाले में भी बोल सकता हूँ ना. If I don't use my convention that left hand side is dependent and right hand side is independent, then I can say that I'll select some value of y that gives me a particular value of x. बोल सकता हूँ ना ऐसा,
Yes.
right?
Yeah.
But what is the exact reason? Okay. So now think of something. Can I say that this is equivalent to this? The first one, is it equivalent to the second one?
Yes, sir.
Yes, sir.
Sure.
No, sir. Y has, in first one, y has a degree of 2 and second y has degree of 1.
So what I'm saying is, if a square is equal to b square, does it mean that a is equal to b? No, no. It means that a can be plus minus of b, no?
Yes, sir.
Isn't it?
Yes, sir.
So the first one is not equivalent to the second one. Okay. The first one, if we, for a given value of x, if we solve for y, we can get two possible values of y. No? For example, if x is equal to 0, y square is equal to 1, that means y can be either plus 1 or minus 1. But in the second one, if I substitute x equal to 0, I'll get y as only 1. I won't get it as plus minus 1. Understanding now?
Yes, sir.
Yes, sir.
So this brings us to another important property of the function. Okay. So you can say, like, see, we will always define a function by a relation. And what is a relation? One way of expressing a relationship is a math expression. Another way of relationship is you can use sets to define. You can have one set of numbers y, another set of numbers x, and whatever values here, You can define some kind of set theory kind of thing that each one points to something like this. That's another way. We can define it in terms of a graph, that some kind of a curve is showing us that for every value of x, there's a particular value of y. So many different ways of expressing the function. Mathematical expression is just one way of expressing it. So, but does any relation qualify as a function? No. We will see why not. Okay, because of this reason only. Y square is equal to 1 plus x square is an example of a relationship. There's no problem with that, because for a particular value of x, it will relate how I can get the value of y. But why that relationship does not qualify as a function, whereas the second one, where I've written y is equal to square root of 1 plus x square, this qualifies as a function. This is because of a very important rule when we are defining a function. Okay, we cannot use any and every relationship to define a function. It has to be a specific type of relation which satisfies this condition that I'm writing down, that for y to be equal to a function of x, okay, they must be defined by a relationship or by a maths relation such that any value of x gives a unique value of y. It should not give multiple values of y. Okay, so such that any particular value of x, that is a dependent variable of x. Now we understand that whatever is x is the variable. So any particular value of x, which is the independent variable, must define a unique or single value of y. Okay. So for example, if I write y is equal to square root of x plus x, okay, now you can see that there's a bit of boundation here, that I cannot select x to be a negative number. X has to be non-negative real numbers. But for any value of x, for any x greater than equal to 0, y has a unique value. Y has a unique value. Okay, so x equal to 1, for example, y is equal to 2. X equal to 2, for example, y is equal to root 2 plus 2, which we can write as approximately 3.414, like this. X equal to minus 2 is not defined only. Okay, but so this qualifies as a function. So therefore, this is a function of the type y is equal to fx. And that function is root x plus x. But now if I take that example which I was talking about earlier, that y square is equal to, let's say, 1 plus x square. Now what happens here is, for any x, y may not have a unique value. In fact, in this case, it does not have for all values of x. Okay. So for example, for x equal to 0, y square is equal to 1, which means y is plus minus 1. For x equal to 1, y square is equal to 2. That means y is equal to plus minus root 2. So such a relation is not a function. This is not a function. Okay, it is a type of relation which cannot be used to define a function. Okay, we can even plot the graph for it and all, but that will not qualify as a functions graph. Okay.
So whenever y
Yeah.
is the degree of 2, it is not a function.
Yeah, that's one way of saying it, that if y has a degree of 2, it's not a function. Okay, but another way of saying it would be, okay, if I were to define y as plus minus of x square plus 2. then this is not a function. Okay, because this is the solution of this relation, that y square is equal to x square plus 2 whole square. Okay. But if I took just y as x square plus 2, this is a function, but this is not a function.
Okay.
So
Thank
in
you.
the first example which you are given, in that we're bound to take a value of x greater than 0. So how is it a function?
Because for every value of x, now we are getting a unique value of y. For every value of x greater than equal to 0, root x is a defined real number. Okay, and it's a unique real number, and we are adding that to x. So the sum is a defined unique real number. No?
So it need not be like even if there is a condition for a value of x, it can be a function.
Yes, yes, yes. But there can be some kind of limitation on x, like in a function like this, y is equal to x square plus x. There's no limitation on x. X can be anything from minus to plus infinity. But in a function like this one, root x plus x, there's a limitation. X can only be non-negative real numbers. So there's no problem if there's a boundation on x. But the important thing is this, the statement that I've written above, that it must be defined as a relation such that for any particular value of x, we get only a unique value of y.
Okay, sir.
You should not get multiple values of y.
Okay, sir.
Okay. So now see why this point is so important. Now, because we use functions to define real parameters. Now. So for example, if I'm defining displacement as a function of time, at a particular instant of time, can a particle have two different displacements? Doesn't make sense, no? At least not in the classical world. In quantum mechanics, it might make sense because it might have a probability of being at two places at the same time. But that's a very different brand of physics anyway, right? But in classical physics, it cannot happen that, like the temperature of a body has two different values at the same instant of time, or the velocity of the moving object has two different values or three different values at a particular instant of time. That cannot happen. It has to have a unique value. So that is why for functions which are primarily used in physics to define relationship between physical parameters, it is very important that the function must be a relation that satisfies this property. Okay, people, the logic is clear now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Okay, very good. Now, next thing, let's move on to understand that apart from a mathematical relation, a function can also be represented by a graph. Okay. So, graphical representation of a function. Now, for this also, just like for writing the expression of a function, we use a convention that left-hand side has the dependent variable and right-hand side has the expression involving the independent variable. So like that, when we draw a graph, we always follow this convention that the vertical axis should have the dependent variable and the horizontal axis should have the independent variable. Okay. Now you might ask why I can't reverse that. Okay. Now at this stage, I can give you the answer in two ways. One is that this is just a convention that the vertical axis must have the dependent variable. Okay. And the horizontal axis must have the independent variable. Okay. Okay. Just go through this once and I'll be right back. Okay, so the horizontal axis we always use to plot the points on the independent variable. So this is a convention, you can say, but again this convention also has a logic, and I'll explain that when we come to rate of change. Okay, now how do we plot the graph given the function? Like if we are going to the absolute basics of how graph plotting is done, that given the function y is equal to fx, we take a set of values of x, x1, x2, x3, whatever might be convenient to us. So let's say n set of values. So correspondingly, we find the values of y, y1, y2, y3, etc. and then we plot these points, or we plot these ordered pairs x1, y1. So you all know this, you have done this, for example, in practical work in laboratory, etc. When you want to show when you got experimentally the values of x and y, and you want to show the relationship between them in a graph, you plot these points with the maximum accuracy that you can on a graph paper. And then you try to join these points with the smoothest possible curve. So, that is the approximate way of drawing the graph, because ultimately what we are getting is the approximate curve that represents, every point that satisfies this relation. Because actually we haven't plotted every point. We have just plotted some specific points, and in between we are doing some guesswork by joining the curves. Okay, so that is an approximate way of drawing the graph. Okay, the exact way of drawing the graph would be obviously the exact way would be impossible to draw perfectly, but basically what is a graph? It is a curve in the xy plane such that every point on that curve, every point x comma y on it satisfies the relation of the function, satisfies y is equal to fx. So it should be like, continuation of points one after the other, such that each and every point. Okay, but from real number theory, you know that there'll be infinite such points actually, because between any two numbers only, like 1 and 2 or 1 and 1.5, or between any two real numbers, there are infinite number of real numbers. So this is a bit like, like a circular kind of definition, that how can I, when there are infinite number of points, how can I define it? Okay. So the idea is that this is what is the exact definition of the graph. Now, practically how we plot the graph is like this, that we take a convenient set of points x1, x2 like this. We find the values of the y coordinate by using the formula of the function, and then we plot these points. And obviously, the more the number of points I've plotted and the more carefully I've joined them with the smooth curve, the more accurate my graph will be. Okay. So the accuracy of the graph in the practical method is subject to how many points I've plotted and how carefully I've been able to draw it. Okay. Theoretically, what the graph is that it's not just a particular number of points, it's infinite points one after the other, which if I draw them, they will naturally join into a curve, which will be the graph of the function. So each and every point on that curve is satisfying the equation of the function. So instead of doing this manually, for example, if we write a computer program, which uses a do loop or something, where the values of x, they change by very small amounts. So if x1 is 1, then x2 is 1.001. Let's say x3 is 1.002. So it increments every time by like this, and it goes up to, let's say, the last one, which is 100. So realize how many points there are. Okay, taking an increment of 10 raised by minus 3, I'm increasing the number by a factor of 100. So I'll have to plot how many points in between, 10 raised by 5 points. So that is not something that we can humanly do, but a computer program can do that. It might take a bit of time, but it can calculate the value of y for each of these 10 raised by 5 points and then plot them on the computer screen, and that will give you a more accurate picture of what the graph looks like. Okay, so that is as far as programming goes, but that is not of concern for us right now, because we are not doing a course in programming. We are doing a course in simple basic calculus here. So in basic calculus, this is the definition of a function, the graph of the function. Now the definition shows that we can't really plot a 100% accurate graph. So one of the ways of plotting the graph is that we take an approximate graph. We draw ordered pairs, and the more the number of ordered pairs we have selected, the more accurate our graph is going to be. So let's look at some common shapes of graphs, which we are going to encounter in physics. Common functions. And their graphs. Now, though it's a very simple function, the first one I'm taking, but it's going to be pretty often used in physics, and that is a linear function. So the linear function is a polynomial which has degree equal to 1. That means it's of this type, mx plus c, or you can write it as like this also. It's a special case of the power series, which we call a polynomial function. If we continue this to some maximum power n, then this type of a function, as you know, is called a polynomial function. or a polynomial expression, but we've converted it to function form of degree n in this case. So for example, if I have degree 2, that becomes a quadratic function. If I have degree 1, it becomes a linear function. So n equal to 1, that is a linear function. So that's why we say a linear function is a polynomial function of degree 1. So anyway, so how does the graph of a linear function look like? It's the simplest graph, as you know. The graph is a straight line. Straight line graph, because it has a uniform slope between any 2 points. y2 minus y1 upon x2 minus x1 is a fixed quantity, which is m, because here m and c, they are constants, as you can see. Here a0, a1, a2, these are all constants. So because of this property of the linear function, that the rate of change y2 minus y1 upon x2 minus x1 is uniform between any 2 points. So that means it's such a curve which has a uniform slope. So how will we show such a curve which has a uniform slope? The only possibility is that it's actually a straight line. And the straight line should be inclined in such a way that we can relate this y2 minus y1 upon x2 minus x1 trigonometrically, and we will see it will become nothing but tan of the angle. Okay. So for example, if I'm plotting the graph of the straight line, let's say y is equal to x plus 2. So here you can see m is equal to plus 1 and c is equal to 2. So that means the point where it intercepts the y-axis, that will be 2 in this case. Okay. And this angle will be such that tan theta will be equal to m, which in this case will be 1, which means theta is equal to 45 degrees. Which also means that if I take any 2 points on the graph and I compare the change in the x coordinate with respect to the change in the y coordinate. Okay, so this all stuff that you're very familiar with, but it's going to become more and more important for us in application. So this is delta y, this is delta x. So you can see that this quantity is equal to delta y by delta x, which remains the same for any pair of points. So it's a straight line. Okay. Another example of your straight line is something, let's say, which has a negative slope. So if it has a negative slope, so I think by now in trigonometry, you would have understood how to calculate tan of an obtuse angle. Yes, you've been doing this in trigonometry. Can you tell me what is tan of, let's say, 150 degrees? Have you done this in trigonometry yet, in maths? If you haven't done, it's no problem, but just tell me if you've done. Anybody?
Sir, minus 1 by root 3.
So how we get this? You know the formula, no?
Yes, sir.
Tan of 150 will be minus of tan 30 degrees. Okay. That is minus 1 by root 3. ASTC rule, no, you must have done.
Yes.
So as you can see, whenever theta becomes obtuse, tan theta becomes negative. So this is a case. So for example, if I take the line y is equal to minus x by root 3 plus 5. Okay. So here, this line will have a slope minus 1 by root 3. So that means tan theta is minus 1 by root 3. That means this theta must be equal to how much? It must be 150 degrees. As we've just seen this formula. Okay. Whereas this y-intercept is plus 5. So it's cutting the y-axis at the point plus 5. Okay. And again, if we compare y2 minus y1 upon x2 minus x1 for any 2 points, this time we will see that that's a negative rate of change, because as x is increasing, y is decreasing. So as x is increasing from x1 to x2, you can see correspondingly y is decreasing from y1 to y2. So we can see that y2 minus y1 upon x2 minus x1 will be equal to a negative quantity, in this case minus 1 by root 3. Okay. So these are just 2 examples of the general linear function. One example showing a positive slope, one example showing the negative slope. But unfortunately for us, this kind of simplicity for functions, that slope is constant, it stops with linear function. Any other type of function, it has a variable slope. That means the shape of this graph is not going to be a straight line, it's going to be a curve, because its slope is going to vary from point to point. And that complexity is what makes it necessary for us to understand calculus. So as I said, once we move ahead from linear functions, life is not going to be so simple for us that the slope will be a constant quantity, which is either positive or negative. Now things start to get a little bit more complex. So let's start with the example of the basic quadratic function. The most basic one, y is equal to x squared. Anybody knows the name of the graph of this? Like the shape has a particular name in maths, in geometry?
Parabola.
Yes, very good. It's called a parabola. It's just a name. Again, if you ask me what is the reason for it, I don't have an answer. There must be some historical reason. You can find it out. So the graph of this function, now I'm just going to draw it first and then I'm going to justify it with some ordered pairs. But basically the graph of this function looks like this. It's got a high degree of symmetry, which means the negative x domain part of it looks like a perfect mirror image of the positive x domain part. So again, I'm not so bothered about drawing perfect graphs. We can always use some kind of software tool to draw perfect graphs, but our purpose is not perfection here. It's just to understand the pattern. So for example, for x equal to 1 or x equal to -1, the value of y is equal to +1. But by the time x goes to 2, the value of y disproportionately increases. So my graph, these 2 points, it might not be so evident, but by the time I'm coming to 3, you're seeing how it's increasing disproportionately. So this kind of shape is called a parabola. And in this case, the parabola is for y is equal to x squared. Now notice one thing over here. At any point on the left hand side for x negative, it has a negative slope. If you draw a tangent at any point, now again, I'm not going into the technicalities of tangent yet, but we had discussed something last time, little bit about tangent. So going by that, if I draw a tangent at any point for x less than 0, it has a negative slope. For x greater than 0, it has a positive slope. Also, you can see that for increasing x, slope also increases. That's how it's very different to a straight line. So this difference, I'll illustrate this with very simple thing, that if we compare the graph of y is equal to x squared, just in the positive side of the domain, if I compare it to the graph of y is equal to x, let's try and figure out how different the two things are. So one graph I'm going to draw here is going to be for the specific straight line y equal to x, which passes through the origin and has a slope of unity. That means the angle is 45 degrees. Okay. If I compare this with the graph of what I'm talking about here, which is y is equal to x squared. Now that graph will, now I'm drawing it roughly again. Okay. So that graph will go something like this. It's not a very good rough graph. Okay. So you see, very interestingly, the two graphs cut each other. Provided, of course, I've taken this one as y equal to x squared. So they cut each other at x equal to 1. But this one slope is changing so rapidly that afterwards you can see the slope is becoming more and more. Whereas this one is having a uniform slope. This has a uniform slope. equal to 1, whereas this one has a increasing slope. Now, how much that slope is, we'll discuss later today. Now, we'll see that if we draw a particular point, we can find the slope of the tangent at that point by using what is called the differentiation of y with respect to x. These are all some of the aspects about the comparison of the two. So physics wise, if you're using this to relate something, for example, one object is moving according to the displacement s is equal to t. So it has a uniform speed of 1 meter per second. And another one is displacing according to s is equal to t square. So it has a uniform acceleration of 2 and an initial velocity of 0. So this is how the distance with respect to time will go, or displacement with respect to time will go. For the initial 1 second, the first one will be ahead of the second one, because you can see this graph is above. But after 1 second, the second one has overtaken the first one. Okay. And also, if we compare the instantaneous speeds, we'll have to compare the slopes. So you can see that somewhere over here, this graph will have a slope which is equal to 1. But before this point, somewhere here, this will have a slope which is less. After this point, everywhere the slope of this graph will become more than the slope of the straight line. Okay, so just by observing the graph, the rate of change, the slope, and all these things, if we are relating those graphs with actual physical parameters like distance and time, or velocity and time, or let's say force with respect to momentum, okay, or later when we study electrostatics or gravitation or things like that, we are relating, let's say, field with respect to potential energy or something like that. We get some information about how the physical parameters are behaving by looking at the graph's pattern also. So that is why that graphical interpretation is going to be something important for us in physics. Okay. So later we will see that using this graph, using the graph of y is equal to x square, if we have any general quadratic function, we can get a sort of pattern of graphs. So for example, y is equal to ax square plus bx plus c. Now, I'm just going to go through this a little fast over here because we're going to do this in detail later. If a is positive, okay, and the discriminant, that is b square minus 4ac, is also positive, then this sort of parabola will have this sort of a graph. It will intersect the x-axis at two different points, and the parabola will be opening this way. Okay. But on the other hand, if something like this happens, that a is positive, but the discriminant, that is b square minus 4ac, is less than 0, then this will have a slightly different type of graph. It will have a similar shape, but this will not be intersecting the x-axis because it does not have real roots. So y equal to 0 does not give you real roots. I'm just giving you a couple of examples. Okay, there are more. Similarly, if we have a situation where a is less than 0, but the discriminant is positive, then a is less than 0 means it will be an inverted parabola, and discriminant is positive means again it will have two real roots. Okay. So all these are parabolas. All these shapes are parabolas, but they have different relationship with the x and y axis. All that depends on the values of a, b, and c. So as we go along, we will see a lot of tricks of how to plot the exact graphs, or at least with some guideline points and all, for different types of quadratic functions or different values of a, b, and c. Because quadratic functions are going to be very important for us in physics, whether we are talking about kinematics or later work by energy or future chapters. Quadratic functions are going to be important for us. So since I'm on the subject, let's look at a quick example. I have y is equal to, let's say, x square minus 4x. So I can see about this, a is plus 1. Okay, that's the first thing. And I can also see what is the discriminant. The discriminant is 16. So it is positive. B square minus 4ac, you can see, because b is equal to minus 4 and c is equal to 0. So b square minus 4ac. So that means it has two real roots. Okay. So how this is going to look now, this is very easy to factorize. So I can write this as x into x minus 4. Okay. So the moment I've written it like this, now if I visualize the graph, I can see that this will cut the x-axis at how many places? At two places. One will be where x is 0, because y is 0 when x is equal to 0. And the other one will be when x is equal to how much? X is equal to 4. Because the second bracket is x minus 4. So this will be a parabola such that it cuts at this point at the origin and also cuts at this point x equal to 4. And because the value of a is positive, so which type of parabola it should be? It should be opening upwards. So this will be exactly this sort of a parabola. So without any calculus, without any ordered pairs and all that, I've just done a bit of guesswork. Okay, and I showed you that this will represent y is equal to x square minus 4x. Okay, and more things will also come in. Like for example, the parabola is symmetric. So this midpoint 2 will be the point where you have the minimum possible value. So put the value of x as 2 over here. You can see that y when x is equal to 2 becomes 2 square minus 8. Okay, so 4 minus 8, so it's minus 4. So this point will be minus 4. So this is also showing you, for example, that the value of y will be greater than equal to minus 4 for all values of x, for x belonging to all real numbers. Okay. So if you're, right now, you're probably not at a stage where you can just look at a function like this one and immediately come up with this analysis. So don't worry. This comes from experience. This comes from learning more about calculus as we go along. But I'm just giving you like a peek ahead that, when we know enough things about calculus, we can do things like this very easily. We can do analysis like this very easily for a given function. Not just for this quadratic function, but for any function, we can do this type of analysis quite fast. This is what calculus helps us with. We can get so much information about that function by just doing this kind of analysis. Okay, so that is the power of calculus. It really opens up the subject of functions also, apart from just rate of change and I'll just leave you with a minute to go through this. Okay. Let me know if there's any doubt in understanding how I converted this formula into this graph using all this information here.
Sir, I have a doubt.
So,
Yes.
uh, uh, you will be explaining after some time that how we drew the graphs of y is equal to x square plus bx plus c, right?
Yes, yes. The general graphs, now I'll be explaining. So this one I've just taken a specific example. Now this is an easy example because it doesn't have this c term. Now c is 0, so it's very easy to factorize it. So we can just observe that when you factorize it, that one is that x is equal to 0 gives you y equal to 0, and the other that x equal to 4 gives you y equal to 0. So that means it's cutting the y-axis, sorry, the x-axis at these 2 points, 0, 4, right?
Yes, sir.
And the other thing is that because the coefficient of x square is positive, no, it's +1. So it should be a parabola that opens like this. It should not be a parabola that opens like this. This would be when a is negative. This would be when a is positive. So a parabola opening like this, cutting the x-axis at these two places, the origin and x equal to 4. So it has to look like a shape like this. So just like I use the technique over here, we'll use more general techniques for any type of quadratic equation, which whatever values of a, b, and c has. But we'll come back to that later. Okay.
For now, what do you have to remember with from
You
this?
don't have to remember anything, but that's the beauty of the physics from now on. You have to understand the logic behind things. You don't have to memorize anything. Okay. So for now, what you have to understand over here is that any quadratic function has a basic shape, or any quadratic function's graph has a basic shape, which is this, which is called a parabola. Okay. Now, depending on, so this is the most basic type of parabola, y is equal to x square. So it has this point at 0 and it opens upwards. Okay. Now, from this basic parabola, if we go to a more general parabola, ax square plus bx plus c, the shape will still remain this. But the point is, it might become inverted. When it will become inverted? When a is negative. Okay. It might cut the x-axis at two places. It might not cut the x-axis. Okay. So all these things depend on the value of the discriminant. Okay, understood now?
Yes, sir. So if we have y is equal to minus x square minus 4x, so it will be an inverted parabola.
It will be an inverted parabola, and for example, that will be a little bit different because y is equal to minus x square minus 4x agar hai. So this is minus x into x plus 4. Na? So this has x equal to 0, y is 0, and x equal to minus 4, y is equal to 0. So this will be an inverted parabola which is cutting the x-axis at which places? 0 and minus 4, not 0 and 4.
Yes, sir.
So this will be this point it cuts, this point it cuts, and it's an inverted parabola. So it has to look like this. So this now will have a maximum value instead of a minimum value at x equal to 2. Okay, and you can check out the values also by just taking values. So when x equal to, sorry, minus 2, okay, what is the value of y we will get? See, it will become minus 4, sorry, plus 4 into plus 2 now. So 8. Okay, so that means y will be less than equal to 8 for all x. That's one thing. Okay. Now also you can see, for example, that if I take some point over here, like 1, y will have to have a negative value. Just check it out. Put the value of x as 1. You can see that the value of y will become minus 1 into 3. Sorry, into 5. Okay. So that will become minus 5. If you take it as 2, it will become an even larger negative number. Whereas if you take any value between minus 4 and 0, you will see that between minus 4 and 0, this bracket is a negative quantity, and this bracket is also a negative quantity. So the product will become positive. Whereas if you take something like minus 5 or minus 6, again you put those values here and it will justify why it's becoming a negative value. Okay, so this example is clear now?
Yes, sir.
Okay. Okay, so like this, there is the whole subject of quadratic functions in maths itself. So you can go on and on about these things and learn more properties. But here our purpose is just to understand that any quadratic function will have a simple shape, which is a parabola. Now that parabola could be either pointing up or pointing down, depending on whether he is positive or he is negative. And it could be cutting the x-axis at two places. It could be just touching the x-axis at one place, or it could be never intersecting the x-axis at all. That all depends on the individual values of a, b, and c. And we will learn further how to estimate these things. Okay. Now back to our basic graphs. For example, another graph we should know is the graph of the cubic function, x cube. So this is the most basic cubic function. So this also has a rather interesting kind of shape. Now, unlike the y equal to x square function, this has an inverted mirror image. So if I take on the positive side, firstly, it will rise even more rapidly, compared to y is equal to x square, because it's x cube. But now, more importantly, on the negative side, it becomes like an inverted mirror image. Inverted mirror image in the sense that for 1, the value is 1. So for -1, the value is -1. For 2, the value is 8. For -2, the value is -8. If I draw it more perfectly, you'll be able to see the symmetry like this. Okay, so it has a reverse or inverted mirror image symmetry. Like this side, its mirror image would have been this on the y-axis, and now we invert this mirror image, so it becomes like this. Likewise, you have all the trigonometric graphs which you are learning as part of maths. So for example, if you look at the graph of y equal to sine x in one cycle of 2 pi, that looks like this. And then after 2 pi, it just repeats itself. So again, the whole thing will go from 2 pi to 4 pi in the same way. In the same graph, if we compare y equal to cos x, so that looks like this now. So trigonometric graphs are also very interesting, and so these are examples of graphs of trigonometric functions. But for example, if I have a more complex trigonometric function, like suppose I have y is equal to sine square x plus sine x. Now that's not something so simple like this graph. Okay, so how we are going to plot this graph? So we are going to need some of the techniques and tricks that we will learn from calculus ahead. So couple of weeks from now, you will see that we have some more techniques through which we can try and plot this graph. But right now, it's not such an easy task. Okay, the best we probably do is to plot this graph. We'd have to actually sit down with a calculator, jot down a lot of points, and plot them on a graph paper and try and join them with a smooth curve. So that would be a very crude and basic way of drawing the graph, which would be very time taking. But now notice one thing, all the examples that I've taken, nowhere the graph is going like this, where a single value of x is giving you multiple values of y. It's not going like this. It's not going like this at all. They're all functions. So this thing cannot happen. This is not a function. It's a graph of some kind of relation, that's okay. But it's not the graph of a function, because a single value of x is giving you multiple values of y. So this cannot happen for a function. Okay, so now having understood a basic idea of what is a function and how we represent a function with a graph, let's come to how we apply calculus to functions. Okay, so calculus, the first part of calculus is something called differential calculus, and differential calculus deals with what we call the rate of change of functions. Okay, so let's start by understanding rate of change. And through that, we will start understanding the first part of calculus called differential calculus. The second part of calculus, as you might have heard, is called integral calculus or integration. So for a function y equal to fx, as we saw last time, we defined two types of rate of change. One is the average rate of change, like we'd seen average speed over there. So average rate of change, it is denoted by the symbol delta y by delta x, and that just becomes y2 minus y1 upon x2 minus x1. So this is the average rate of change for an interval, of x, x1 to x2. Okay. Now how we'll calculate the value of y2 is nothing but the value of the function at x2. The value of y1 is nothing but the value of the function at x1 divided by x2 minus x1. So we have a very simple formula for average rate of change. It is y2 minus y1 upon x2 minus x1, which is calculated this way. Okay, so let's understand this with a quick example. Suppose I have the function y is equal to x squared minus 2x, that function that we had taken earlier today. Okay. Now I want to find the average rate of change for first interval I'll take is x equal to 0 to 1, let's say. And second interval I'll take is x equal to 1 to 2. So let's just apply the formula here and see what we get. We don't need to plot any graph or anything. So for the first one, we can see that delta y by delta x is f of x2 minus f of x1 divided by x2 minus x1. So here x1 is what? 0. So f of x1 becomes how much? It becomes f of 0. So that is 0 square minus 2 into 0. That's 0. Whereas x2 is 1. So f of x2 is nothing but the value of the function at x equal to 1. Now what was the function? The function was this, x square minus 2x. So the value of the function at 1 will become how much? 1 square minus 2 into 1. So that's minus 1. So we can see that this is my y2, this is my y1. So this thing will become minus 1 minus 0 divided by 1 minus 0. So as you can see that the average rate of change is becoming minus 1 for this interval. Delta y by delta x for x equal to 0 to 1 is becoming equal to minus 1. So that becomes my final answer. Okay, so this is how we implement the formula for average rate of change. It is y2 minus y1 upon x2 minus x1, where y2 is nothing but the value of the function at the point x2. y1 is nothing but the value of the function at x1. So that divided by the interval. Okay, so just make a quick note of this if you like and work out this second part and send me the answer. Send me the answer on chat message preferably, okay, so that others also have a chance of calculating it.
So may I leave the meeting and join again because I'm not being able to send messages.
Okay, sure. Yeah, so calculate the B part of this question and just send me the answers on text. Yeah, many of you sent, that's correct. Very good. Anirudh, Atharv, Bhavika, your answers are correct. Kirti, correct. Yash, correct. Archit, just check your calculation once, beta. Ashley, correct. Okay, so I'm just giving the final answer. Okay, so most of you have got the answer correct. Okay, so let me see. So for the B part, we are taking x1 as 1 and x2 as 2. So y1 will become f of x1, that is f of 1, which we've already calculated here, which is -1. Okay, whereas y2 will become f of 2. So what is the value of the function at 2? It is 2 square minus 2 into 2. So it's interestingly 0. So this time when we calculate delta y by delta x, that is f of x2 minus f of x1 divided by x2 minus x1, we are getting 0 minus of -1 divided by 2 minus 1. So interestingly, we are getting +1. So the average rate of change in the second interval, which I have taken 1 to 2, is in fact 1. Okay, now this whole result is going to make a lot of sense for us in just a moment when we look at the graphical interpretation of average rate of change. As you must have guessed, based on what we've done last time, the average rate of change in terms of graph is nothing but the slope of the secant line. Graphical representation. In fact, we will call this interpretation, graphical interpretation. Okay, so let's say a particular function, whatever it is, it has a graph like this. And I have selected my points x1 and x2 over here. So correspondingly, this is the point on the graph which has an x coordinate of x1 and corresponding y coordinate y1. And similarly, this point has coordinates x2 comma y2. So I can see that this interval here is nothing but delta y. It is y2 minus y1. And this interval over here is nothing but delta x or x2 minus x1. So the ratio of these two things, which is the average rate of change, is nothing but the slope of the straight line joining these two particular points, x1, y1 and x2, y2. So that kind of line, as we've seen last time, is called the secant line because it cuts the graph at two distinct points. So the graphical interpretation is that average rate of change is slope of the secant line. It is this tan theta. And specifically, what is the secant line? The secant line is the straight line joining the 2 points x1, y1 and x2, y2 on the graph. Okay, so let's also look at that particular example of the quadratic function that I had taken. Y is equal to x square minus 2x. This was the function, and I wanted to calculate delta y by delta x for x equal to 0 to 1 first, and then x equal to 1 to 2. So let's see how the answers make sense. So when we look at this equation now, we can see it's a quadratic equation which has a positive coefficient of x square. So a is positive, okay, and we can see that x equal to 0, y is equal to 0, x equal to 2, y is equal to 0. Okay, so that means it cuts the x-axis at the origin and again at the point 2, which is, let's say, over here. So the graph has to be of this kind of shape. So parabola opening upwards. So it has to be in general a shape like this. Okay, so naturally, this is the point where it reaches its minimum value. You can see if you put x equal to 1, you get the value of y as minus 1. Okay. So now naturally, if I draw the tangent line, the secant line from this point to this point, this will have a slope of minus 1. You can see now it's going from 0, 0 to 0, minus 1, or rather 1, minus 1. So can see that for this interval, the average rate of change is without a doubt -1, which I had got by formula also. Whereas if you look at the second interval that I had taken, which was 1 to 2, so there, this is your secant line. Now if you notice this secant line, it has a slope equal to +1, because again this point is 0, 2, and this point is 1, -1. Okay, so this one should have a delta y by delta x equal to +1. So this is just showing you in practice that how it all works. Whatever we are seeing in terms of formula, how it works with respect to the actual graph also. Okay, so this is about instantaneous rate of change. Sorry, this is about average rate of change. Now we come to the second type of rate of change, which is the more abstract one, the instantaneous rate of change. So we had seen some kind of approximate definition of it last time in terms of instantaneous speed. But now today onwards, we will look at the perfect calculus definition of it. Okay. So in terms of calculus, for a function y equal to fx, the instantaneous rate of change is given by a special symbol now. You might have seen this symbol dy by dx. You can read it as dy by dx, but it is read as differentiation of y with respect to x. Okay, and the definition of this term is that it is delta y by delta x, but with a special condition which we call the limit, that delta x is tending to 0. So instantaneous rate of change is the rate of change at a point x equal to x, not for an interval. Okay, and for what we call an infinitesimal delta x. So infinitesimal means that it is tending to 0. It's extremely small, so it is tending to 0. Okay, so now talking further about this infinitesimal rate of change or instantaneous rate of change, we will see that there are two ways of interpreting this. Okay. One is the algebraic meaning. What does this mean in terms of algebraic terms? Okay, let's understand that. So for the algebraic meaning of this, we'll just make use of the definition. What is the definition of instantaneous rate of change? It is equal to delta y by delta x, but under the special condition that delta x should be tending to 0. So that condition is called a limit. Okay. So what this means is that we are looking at rate of change from x1 equal to x to x2 equal to x plus delta x, but that delta x is so small that it is tending to 0. Okay. So here we use another term, that dx is equal to limit delta x tending to 0 delta x. So the term dx, it is given a special name. It is called a differential change. It's called a differential change in x, which means it is a very, very small change in x. Extremely small change. Such a small change that it tends to 0. So we're talking about the rate of change of y with respect to x from this x1 to this x2. Okay, so let's see further how we'll implement this now. So this dy by dx, we'll have to calculate this limit that delta x is tending to 0, and in that condition we have to find delta y by delta x. Okay. Now when I'm taking x1 as this and x2 as this, okay, so according to this information here, what I'll take y1 as, I'll take it as f of x1, so that is fx. What I'll take y2 as f of x2, which is f of x plus delta x, but again under the condition that delta x is tending to 0. So this will become f of x plus delta x, that is y2, minus y1, which is f of x, divided by x2 minus x1, which is delta x. But this whole thing has to be calculated under the limit that delta x is tending to 0. So this becomes the algebraic definition of dy by dx. This becomes the algebraic definition, and I'll show you how we calculate it also.
So what is the limit? Can you please explain again?
So see, we are calculating the rate of change of y with respect to x from x1 to x2, where x1 is what? The instantaneous value of x, that is x only, And x2 is what? A value of x that is very close to x. That means it's x plus delta x, with delta x tending to 0. Is this point clear?
Yes, sir. That is clear.
Okay. So now if this is x1, then what is y1? It is the value of the function at x1. So substitute x1 as x. So this is my y1.
Yes, sir.
So this is my y2 now. Clear now? Substitute x2.
Yes, sir.
So now what is my delta y by delta x? It is y2 minus y1 upon x2 minus x1. But when I'm calculating delta y by delta x for this special condition, I should substitute these as this. So that's how the numerator is becoming f of x plus delta x minus fx, and the denominator is becoming just delta x. Clear now, na?
Yes, sir. But why are we writing the limit? If is it
Yeah,
fine?
because that is the condition, na? Because we are calculating not delta y by delta x, we are calculating dy by dx. So dy by dx by definition is delta y by delta x for this limit. Na?
Okay, okay, sir.
No? So ultimately what we are calculating is not delta y by delta x, we are calculating dy by dx. And dy by dx is by definition instantaneous rate of change. That means it is with the limit that delta x should be infinitesimal or a differential change, or should be delta x tending to 0.
So dy by dx is only applicable when delta x tends to 0.
Yeah, I mean, in other words, how do we calculate dy by dx? By making delta x tend to 0.
Okay, okay.
You're understanding, na? If delta x is not tending to 0, then it's an average rate of change. But when I make delta x tending to 0, it converts from an average rate of change to an instantaneous rate of change.
Okay, sir.
So let's say you are measuring average speed. So you're measuring average speed for an interval of half an hour. So it's fine, it's average. Then you reduce the interval to 1 minute. That's also fine. You reduce it to 1 second. It's also fine. But the moment you start reducing it to 1 millisecond or 1 microsecond, now you are going closer to the value of instantaneous speed instead of average speed. So the smaller the value of delta t you're making in that case, the closer you're coming to the exact value of instantaneous speed.
Okay, sir, I got it.
So it's an abstract idea. No? When we write it like this, it's abstract. But when we convert it to the geometrical picture next, it will become a little bit more easy to understand what we mean by instantaneous rate of change. The secant line will convert to the tangent line because the 2 points we are considering will become more and more merged into 1 point as delta x is tending to 0.
Yes, sir.
Okay, so having made this definition over here, the algebraic meaning of it, we are still understanding that it's quite abstract. As of now, we don't have a clear-cut method from this, but that the interesting thing is, while it is so abstract, when we start developing the maths of differential calculus, even this abstract concept will give us a very simple formula of how to calculate the rate of change of a given function. So that is the beauty of differential calculus, and we are coming to that very soon. Okay, so let's look at a quick example of how we might apply this. Okay. Calculation of dy by dx from algebraic definition. Okay. So this is the example we are looking at. And what is the algebraic definition? The algebraic definition is this, that it is f of x plus delta x minus fx divided by delta x under the limit, okay, that delta x is tending to 0. This is the algebraic definition. Let's see how we can apply this in a particular example. Okay. So in my example, suppose the function we are talking about is x cube. Okay, this is the function. Y equal to x cube is my function. Now I want to find out instantaneous rate of change. How I'll find out? So I'll apply this definition. So the instantaneous rate of change will be limit delta x tending to 0 f of x plus delta x minus fx divided by delta x. Now here, what is my fx? My fx is x cube. So I'll just substitute. Okay. So the first term here, so LIM is the short form for limit. Okay, you must have understood by now. So x plus delta x, the value of f will be replaced with what? Cube. So x plus delta x cube minus x cube divided by delta x. Now see, when I'm trying to solve this, if I put delta x as 0 directly, what I'll get? I'll get 0 by 0. So I can't define that only. So that means I have to somehow solve it further till I get some logical answer, or I get some valid answer for the value of this expression, substituting delta x tending to 0. So for that, what I'll do next is I'll open this bracket using expansion. So use the a plus b whole cube expansion. So this bracket becomes x cube plus 3x squared delta x, okay, plus 3x delta x squared plus delta x cube minus x cube divided by delta x. Still, if I substitute delta x 0, I'll still get 0 by 0. So I have to do something further. So what I do next is I solve this little further and I cancel off the x cube. So next step, what I'm getting is 3x squared delta x plus 3x delta x squared plus delta x cube divided by delta x. Still, if I put the limit, I'll get 0 by 0. So I have to go one step further. Now we come to the very critical step, that if I take delta x common in the numerator, okay, I can write the numerator now as 3x squared plus 3x delta x, okay, plus delta x square. I can write the numerator as this. Now the very critical step, and listen very carefully, delta x is tending to 0, but delta x is not equal to 0. It is not equal to 0. So as long as it's not equal to 0, I can say ratio of delta x by delta x is 1. If it was equal to 0, then I can't say, because it would be undefined. But the point here is that delta x is a very, very small number. You can't imagine it's that small, like 10 raised by minus 20 crores or something like that. So it's so small that we can't imagine. For all practical purposes, it's 0, but it's not exactly equal to 0. So as long as it's not exactly equal to 0, we can define delta x by delta x as unity. We can cut it. So what I'm left with this now. So next step, now I can put delta x tending to 0 inside the bracket. And from that, I can say that these terms will become negligible. The second and third term will not matter because that delta x is that small. It's like 10 raised by minus 100 or 10 raised by minus 1000 or something like that. So these terms, they will become tending to 0. So what I'm left with 3x squared. So finally, this is my conclusion, that dy by dx for this particular value of y will be, so that means the differentiation of the term x cube by algebraic definition I'm seeing how it reduces to 3x square. Okay, so more about the interpretation of this I'm coming to, but first just go through this stepwise process. I know it will seem very lengthy in the beginning, but we will develop shortcut methods in this also. The first important thing is the concept. So for the given function y is equal to x cube, how I am going to get the value of dy by dx by algebraic definition. Okay. From algebraic definition. Okay, so this is the algebraic definition. So how I'll apply this over here for this particular function, and we'll come to the conclusion that dy by dx or instantaneous rate of change at any value of x is equal to 3x square. Okay, so hope you are going through the steps very carefully. Please let me know if there's any doubt in any one of the steps in between. Okay. Now let us look at the other way of looking at it, the geometrical interpretation of instantaneous rate of change. Okay, so again, this is going to be a bit of an abstract business, okay, but it will give us a bit more clarity about what we are doing, at least from a visual perspective. So just remember what we discussed about the meaning of a graph earlier, that the graph of a function is nothing but it is a collection of points after all, which are all satisfying the equation of the function. So if I draw a point x equal to 0 and y happens to be 0, so it will start from the origin. But then if I draw the next point very, very close to 0, so it's 0.0001 something, and find the value of y, then the next point 0.002, and like that I keep drawing point after point, then that collection of points naturally fits into a curve, and that curve is the graph of this particular function y is equal to fx. Okay. Now I want to find the instantaneous rate of change at a particular value of x. It's not for an interval, it's for a particular value of x. So let's say that particular value of x is here. This is x. So the particular point on the graph is this. It has a y coordinate and an x coordinate such that the two satisfy this relation that y is equal to fx. Now I want to find the instantaneous rate of change. So for that, what I'll have to do is I'll have to zoom into this as much as possible, because I'm talking about a very small change in x. Okay. So this is the point where x is equal to x. Okay, this particular point over here. Okay. Now I'll have to imagine that I have another point which is very, very close to this. So let's say that point is this one. It's so close that it's almost merging. So when I look at the x coordinate at this point, I'm only shifting along the x-axis by very, very small amount. And correspondingly, the change in y will also be very small, because the change in x is very small. So this change in x over here, you can see, this is the differential interval dx, which is basically equal to delta x with the limit that delta x is tending to 0. And this corresponding change in y is dy, which is nothing but delta y with a limit that delta y is tending to 0. Okay. So now if I basically try to join these 2 points with a line, the type of line I will come across will be a very different line. It will be what we call the secant line. It will be what we call the tangent line, because when I zoom out of this diagram, these 2 points are going to merge into one point. They're not going to be separate points. So that is why this line will no longer be called the secant line. It will be called the tangent line if I have drawn these 2 points perfectly. That is, they are so close that they are almost merging with each other. So if I've done that successfully, then this line that I'm drawing here, that becomes successfully what we call the tangent line. So this is the tangent at x equal to x. Okay. And the slope of this tangent will become nothing but our instantaneous rate of change. So when I zoom out of it, you can see that you can hardly see those 2 points as separate points. The more accurately I'll be able to draw this diagram, the more these 2 points are merging into one point. Okay. So the interpretation of this becomes that it is the slope of the tangent line. That is the geometrical interpretation now. Instantaneous rate of change is equal to slope of tangent. Okay, so just a while back, we had seen the example that for y equal to x cube, we had got the value of dy by dx was 3x square. We had got this by algebraic method. So let's see the interpretation of that graphically. So what it means that, this means that for the graph of y is equal to x cube, the slope of tangent at x equal to x is equal to 3x square. So for example, at x equal to 1, the slope should be 3. At x equal to 2, the slope should become 12. At x equal to minus 1 also, the slope should be equal to 3 only. At x equal to minus 2 also, the slope should be 12. Let's understand how this relates with respect to the graph. So we had seen the interpretation of y is equal to x cube graph earlier. So it was something like this, let's say. Okay. So you can see that this graph is such that at x equal to 1, if I draw a tangent, it's like this. So according to this information, this tangent should have a slope equal to 3. Okay. But if I draw a tangent at x equal to 2, it should have a very different slope. It should have a slope which is considerably larger. For example, if at x equal to 2, I draw this tangent. This tangent has a slope of 12. You can see the slope is increasing rapidly. But similarly, if I go on the negative side, and if I draw the graph a little more carefully, you'll be able to see the symmetry. To see the symmetry. If I draw the tangent here, it's still a positive slope. See, still a positive slope. But as I go further away, the value of the slope is increasing. So now all this starts making sense now, right? Okay, so now that we have understood instantaneous rate of change in two ways. Okay, one is from the algebraic definition point of view, that it is f of x plus delta x minus fx divided by delta x. Okay, limit delta x tending to 0, or we have understood it from the geometrical meaning, that it is slope of tangent. But these are two very abstract ways of defining it. Okay, the first, the algebraic definition, involves a lengthy solution for it, and the second is a very abstract idea. It's not really practical to draw the graph and find out the slope of the tangent. So we come to a separate method altogether. Now we understand instantaneous rate of change from a process called differentiation. And from here, life will start becoming easier as far as instantaneous rate of change is concerned. Okay, differentiation, or the principles of differential calculus. So these are basically a set of methods and formulae related to those methods for rate of change. For calculation of rate of change, they give us a set of methods and techniques and formulae. Okay. So the first thing we learn in this is the differentiation operator. It's like any other mathematical operator. It applies on something and gives us an output. So this is the differentiation operator. This is the symbol for it. So this is read as differentiation with respect to x. Okay. So if I apply this operator on a function, so this is now differentiation of that function with respect to x, or I apply it to another variable. So this is now differentiation of y with respect to x. Okay. So what this differentiation operator does is it operates on a function of x to give the rate of change of that function. And by rate of change, we mean instantaneous rate of change. It directly gives us that quantity. So instead of doing all that algebra, we just use that operator. Once we learn the rules and formulae related to this operator, so we can directly apply it, and it will give us the instantaneous rate of change. So we can think of this differential operator like a box which operates rate of change Okay, and when we input the function y equal to fx, the output that we get from this by applying that operator is the rate of change of that function. So this is the rate of change. So it applies on a function And on application on the function, the operator gives us the rate of change of the function. Okay. So just at an introductory level today, we'll see the most basic formula of differentiation. Differentiation of x to the power n is given by the formula n into x to the power n minus 1, where n is any real number. Okay. So for example, by this formula, differentiation of x cube will become 3x to the power 3 minus 1, 3x square, which we have seen before. Okay. Differentiation of x square will become 2x to the power 2 minus 1, or 2x, which is also something we have seen in the last lecture indirectly. Then, for example, if we have y is equal to square root of x and we want to find dy by dx. So again, what we'll do here is we'll express differentiation operator applied to root x. Now root x will be expressed as x to the power half. So by applying this principle now, this will become 1 by 2 x to the power half minus 1. So that is 1 by 2 into x to the power minus half. So I can write that as 1 by 2 root x. So this becomes the answer. So this is dy by dx when y is equal to root x. Now we will see a proof of the formula also at some stage, and it will be based on binomial theorem, just like we have seen the proof of this one today by expanding a plus b whole cube in that algebraic definition. But for us right now, the proof is not so important. The more important thing is the direct application of this. So this is the first formula. Now the second thing is that if we are differentiating a constant multiplied by a function, you can always take the constant outside and multiply it with differentiation of the function. So for example, if y is equal to 3x to the power 4, then differentiation of y with respect to x will become differentiation operator applied to 3x to the power 4. Now 3 is a constant here, so 3 will come out. So it will become 3 into differentiation of x to the power 4. And for differentiation of x to the power 4, we'll again apply the x to the power n rule. So this will become 3 into nx to the power n minus 1. So as you can see, this will become 12x cubed. So dy by dx in this case will become 12x cubed. This is how we apply this. Then very similarly, another term we'll use is that differentiation of the sum of two functions. Sum or difference, in fact, is now this is just like the distributive property. We can open this bracket and apply the differentiation operator separately to each one. That will apply even if this is a minus sign. So for example, if y is equal to x cube plus x square, then dy by dx will become differentiation operator applied to x cube plus x square. So that will, from the above principle, like a distributive principle, it will become differentiation of x cube plus differentiation of x square. And then we apply the x to the power n rule. So this becomes 3x square and this becomes 2x. So ultimately our dy by dx becomes like this. So you'll see that by using the above x to the power n formula and by using these two properties over here, this one and this one, you can literally differentiate most algebraic functions quite easily by using these two, or rather these three. Yes, very good, Bhavika, that's correct. And as an example of this also, for any linear function, the differentiation becomes equal to what? It becomes m, which is the slope. Because it has a common slope. Okay. Slope of tangent, which is the same thing as the secant line, the same thing as the line itself.
So what if we have?
Sorry, come again, Veda. What if?
So what if in the above example we have y is equal to x cube plus x square plus 1?
So we'll just apply this principle. Y is equal to x cube plus x square plus 1. So we want to find dy by dx. So we'll first apply the operator on this thing. Okay. Then we'll separate each out of the terms. Now the one might be confusing you initially, but there are a couple of ways of understanding this. One is a constant, so its derivative should be 0, right? Rate of change of a constant is 0.
So I didn't get you.
So see, how does the constants graph look like? It looks like a horizontal straight line.
Yes, sir.
So what is the slope of a horizontal straight line? It's 0.
0, yeah.
So that's one way to understand. So if we write differentiation of a constant, so this is any constant, this should be 0. Why? Because if we have the graph of a straight line, which is a constant function, so this is the function y is equal to c. No? So it has a slope of 0. Whereas if we have y equal to mx plus c, it has a slope of m. So we draw the tangent line or secant line at any point. All of them have the same slope, which is equal to m. Whereas for a constant function, the slope is 0. So that's one way to understand. Another way to understand is that x equal to 1 can be written, sorry, y equal to 1 can be written as x to the power 0. So differentiation will become what? 0 into x to the power minus 1. So that's 0. But this is an unnecessarily complicated way. The very easy way to interpret is any constant function, not just one, is a flat line. It's a horizontal line. So the value of y is not changing at all. So its rate of change should be 0. So separately, the rate of change of this term d by dx of 1 should be 0. Or even if this had been 5, okay, even if this had been any other value, even for this, what will be my dy by dx? It will be rate of change of x cube, which is 3x square, plus rate of change of x square, which is 2x, plus rate of change of 5, which is 0, because 5 is a constant.
Okay, yes, I
Okay.
got it.
Got it now? Understood? Okay.
Yes.
So we will conclude today's session here. Okay. And through this, you will see that you'll be able to solve a lot of basic things in differentiation, like all polynomial functions or basic algebraic functions. You'll be able to differentiate by using these 3 or 4 simple principles. The formula for differentiation of x to the power n, nx to the power n minus 1, and then these simple things that a constant multiplied by a function, we can differentiate by just taking the constant outside, or the sum or difference of two functions, we can just differentiate them individually and then add or subtract the rate of change. Okay. So hope you have enjoyed today's class and understood everything. Please revise the lecture notes and the recording when I send it later very carefully. And if there are any doubts, firstly in the revision part only, send it to me. I will help you with some hints and discussions. Okay. Then there will be another assignment sheet along with the first assignment sheet, which I've already sent. So please go through the first sheet also once more, and now the second sheet. And if any doubts are remaining, please send them to me. If you have joined the Discord platform, then you can send the doubts on the physics doubts page on the Discord platform. It will be a little bit more organized for you as well as for me. Otherwise, you can always send it on WhatsApp also. There's no problem with that. So that's it for today, people. Wish you all the best and thanks for attending.
Thank you, sir.
Thank you,
Bye,
sir.
sir.
Thank you.
Thank you,
Sir,
sir.
bye, sir.
Thank you, sir.
Thank you, sir.
Bye, people. Bye.
Thank you, sir.